later after we finish this class. Okay, so if, like, let's say I have, as I show you the other day, this crane that I have here. Okay, if I said I want to know what are the support reaction at this pin here, if I have 100 kilonewton force being applied to this hook here. So you must, as an engineer, all right, you look at it, okay, I know how to do this. You draw and you know with pin support, what are the reactions. So pin support will try to resist, will stop it from going on the X direction and Y direction, but it will not stop it from rotating. So you know that that's how you should put the reaction force for pin. Okay, so if you are about to draw, for example, bridges, the section of bridge, and the support is roller support. So you want to be able to draw that, and you know that for roller support, we know that it will not prevent, it will allow motion in X direction, and it also will allow motion, rotation, but it will stop it from moving upward in X direction, upward or downward. Okay, so we must know all of those. And for fixed support, so I have one friend the other day of your friend said that when you learn statics, your fixed support, the symbol for fixed support is always in inside the structure or in the ground. So I think it will look like, if a pole with fixed support, it will look like something like this. This is what you learn in statics, right? So it shows that it is inside. But as I showed before in the previous slide, this also means that cantilever beam is always representative for fixed support as well, as you can see in the previous. So in this, this is the symbol for fixed support. Okay, so it doesn't matter if it's inside or it's on the floor. You must know that this is not just that pole being put on the floor. Okay, it is a fixed support. It will prevent the all the direction, motion in translation or rotation. So be familiar with all of this. Okay. All right. So now we know all of this. We know how to procedure to start analyzing static equilibrium problem. So as you can see here, this guy, the stilt walker in standing position. So he has balance. Okay, all forces acting on the walker balance out. No change on its translational motion. In addition, torque acting also balance out, and that's why he did not topple. Okay, so in life, everything you can analyze using static equilibrium equation as well. So that's how engineering mechanics is used in real life. Okay, so the condition for static equilibrium, why is it important? So it is an important concept in design of countless rigid structure, from the floor of the system, floor system of a house to a normal suspension bridge, because this structure must maintain static equilibrium under all expected loading condition. So whatever design that you have, you must analyze it using static equilibrium. You want it to be stable. So in this case of this crane here as well, we must know what are the limit for this. Okay, so as an engineer, you must be able to calculate that. So if I have a pin support here, okay, this pin support is made of certain materials. These materials can only sustain this type of stress. So it will start to deform if I put a load here exceeding certain amount. So you must know all of those. That's why you study statics and also mechanics of solids. All right. So these are the three static equilibrium equation for rigid body. So this is for 2 dimension. When the body is subjected to a system of forces, which all lie in x and y direction, then the forces can be resolved into their x and y, okay, component. So this is the Brignon theorem. So these are the three equations that we are going to use extensively in this course. All right, so the procedure to analyze the problem involves static equilibriums is that when you look at a problem, you draw its free body diagram, okay? So sometimes we have at one point, there's two unknowns. So we draw free body diagram, we get all these support reaction, we have the unknowns, okay? So when we have two unknown at one point, I would suggest that you take moment at that point. So you can cancel out that two unknown first. Okay, so you try to find the other unknown first and let that take moment at the point where there are two unknowns. So apply the moment equation of equilibrium about a point O that lies at the intersection of the line of action of two unknown forces. So when the line of actions are passing through that point, the pivot point where you take your moment, it will cancel out. Okay, so start with that, and then but sometimes I start with x and y either as well. So whichever you are convenient with. Okay, so if you, let's say you draw your free body diagram, you have three unknowns, so automatically you can solve it straight away. So I have three unknowns, I have three static equilibrium equation, I can solve it. Okay, but if you cannot solve it, if you have four unknowns for one free body diagram, so what you need to do is to look at other member of that problem that you are analyzing. Okay, so if there's another member, then you can draw that member, and that member will carry another three free body diagram, three static equilibrium equations. So that's how you analyze it. So if you have three in one free body diagram, you can solve it straight away. So when applying the force equilibrium equation, Fx and Fy, orient the x and y along the lines that will provide the simplest resolution of the force into the x and y component. So if this is like if you have a structure like this, okay, and there are force going this way and there's a force going that way, and this is a pin support. So we know pin support will have x and y. But you can deduce this since you can see that all of the other forces are perpendicular to this member. So you can assign your x and y instead as this. So this is my y prime, x prime. So you can solve it like that. So now you can sum forces x equals to 0. And you can say that this is how I take that. The new coordinate system is this one. So you can look at your member and look at how the applied force being applied. So in this case, all the external force are applied perpendicular to that member. If you try it, I have one question that I gave you in homework C1 lesson 3. You try both way. Try it this way, solving it this way, like what I assigned here, and try to solve it like this. And you will see that the answer that you get if you solve it with fx and this is ax and ay, the resultant of this is going to be equal when you solve it like this as well. So you might not have, you will have more understanding when you try to solve this by yourself. Okay, so there's one question in homework 3, homework C1L3. I give this kind of question. I'm sure you've probably already learned this in static as well. Okay, so if the solution of the equilibrium equation yield a negative scalar for a force or couple moment magnitude, this indicate that the sense of opposite is opposite to what you have assumed in your free body diagram. So this is, I'm sure everyone knows this as well. If you draw your free body diagram, you can assume the direction of forces in your free body diagram, whichever direction you want. Okay, so you draw, you said that I have, this is my free body diagram. I have external force going upward, external force going downward, and here I have fixed support. So with fixed support, we said, okay, it's going to resist in X direction, it's going to resist in Y direction, it's also going to resist rotation. So you can assign this whichever direction you want, but when you do your calculation and you get negative, it means that what you assume here should be the other way around. So that's how we analyze the reaction, static equilibrium equation. So I have solved this in Instagram, step by step on how to do this. So I have given you the link yesterday. Now I want to ask if anyone have any questions regarding this one. So those who just joined, I have provide the link to Instagram as well. So the video is about all the videos is about all the example. I will try as much as possible. Okay, I have a lot of other things to do as well. So I will do all the example in the lecture notes, and I will provide the video in Instagram. You go and watch that, and if you have questions, you ask me in the class. So this is simple. As I said, in the video, you are asked to determine the tension in the chord at C and the horizontal vertical component at point of friction point at point A. So this is pin. So pin, we know it will resist X and Y direction. AY, AX. So you are asked to find the tension of this. So what you can do, there are two steps. What you can do is you can draw the free body diagram of the chord, but you can also draw the free body diagram of the pulley. But we know that according to Newton's third law, if an object A exerts a magnitude of force to object B, the object B exert the same force to object A as well. So here, the distributed load will cancel out. So you can assume that it's internal forces. Okay, so it will cancel out. So it's not going to be included in your calculation. So when you calculate that you sum forces, you will get that did I sum force or sum moment? Yeah, I sum moment at point A, I will get that the tension of the wire here at the cable at C is going to be equal to this one as well. And then you can start doing the summation of X, the force in X and Y direction. So be familiar with, as an engineer, with if people ask you, what's Newton's first law? What's Newton's second law of motion? What's Newton's third law of motion? It should be at the top of your head already. You must know this already. Okay. Like last time in the first class, I asked you to state what Newton's first law of motion. Some of you very good, you know that. But if you don't know, it's fine as well. You are a generation, a Google generation. You all can search and try to understand it. So if, let's say, a football player, Syahir lah main bola sepak, okay? When you kick the ball, you are applying certain force to the a magnitude of force to that ball, okay? And the same time, that ball is going to exert the same force, but different direction to your foot as well, Okay, so that's Newton's third law. Okay, so that's how you solve question C15. Go and watch that video. Any questions you want to ask, you can leave the comment there. I will check it on a regular basis. If you have question, I will answer you there as well if it's possible. Okay. So we've solved this. I think you guys already know statics as well, so there won't be any problem with that. I have solved this as well as well. So determine the reaction at the fixed support shown in figure 22. So fixed support, again, what's going to happen when this load is being applied at rest? This will be at rest as well. It's not going to not going to react, right? So when we have load being applied to this member, what's going to happen? This support is going to stop it from going to X direction. It's going to stop it from Y direction, A, Y, A, X, and it's going to stop it from rotating as well. So draw that free body diagram. So this free body diagram is easy. You just replace the fixed support with this reaction forces. And then you sum and you can see now you have three unknown. I have 1, 2, 3, 1 unknown, 2 unknown, 3 unknown. So I have 3 unknown now. And I have 3 static equilibrium equation. Straight away, you can solve this. Okay, so sometimes you have frames. Maybe you have frames looking like with roller support here, and it consists of 2 member. Okay, you are asked to find the reaction force, and then you have this. Sorry lah, my drawing is very ugly. Okay, and a force being applied here. Okay, sometimes you can see that here you have x x and y, and here you only have x ay ax, and here you have by. Okay, so you have three unknowns, and you have 3 equilibrium equations. So you don't have to dismember this. Okay, you can solve it straight away because whatever happened here, it will cancel each other. So not necessarily when you have, I will give you one question. Remind me, I have found this question that students have problem because when they start putting all these reaction forces. Okay, because what you learn from static is that you have to dismember this. You need to dismember, and that so you have to draw the free body diagram of this or free body diagram of that to solve this. But look at this frame as a whole first. Put all the reaction forces. If you have 3 reaction forces, you have 3 equilibrium equation. You can solve it straight away. So remind me to give you these questions. Last semester, I give these questions to students. I think almost all of them did not get it right because they dismembered it. So when you dismember that, there is a possibility you will get something wrong there. So your calculation will start to be wrong all over as well. Okay, so analyze the member first as a whole. And then if you have 4 or 5 unknowns, you know that you need to dismember them. But if you have 3 unknowns, you can solve it with the 3 equilibrium equation. Okay, so go have a look at this in Instagram. Okay, maybe I should ask your opinion. Is it okay for me to give that step by step in the video as a solution for you? What do you think, those who already watch it? I think it is great. I think okay, very clear. Okay, so it won't take your time, too much of your time to watch each video. So you can give a video, watch a video of 8 minutes for if you have waiting for your anime from one episode to the other one, so you can watch it. Okay. So I'll try as much as possible to do that for you. Okay, so those who has not looked at it yet, go have a look. Okay, all right. So I've discussed that, and I have discussed this one as well. So with this one, as I have mentioned just then, so these questions ask you to determine reaction at pitch support A and also a force in the hydraulic arm BD for the truck crane as shown in this figure here. Also, I have many toys in my office. So it's, for example, this is the member that we are talking about. Okay, so this is the member that we're talking about. As an engineer, you should be able to draw this member. So this is how I model this. So this is the idealized model. And I want to know when there is an applied force being applied to the hook of 900 pound, and also there's a concentrated moment at point A was given to you. So you are required to find the reaction at point A of the truck at the point at pin support A, and also at the hydraulic arm. And you also need to identify the hydraulic arm is either is in compression or is in tension. So with this one, as you saw the free body diagram in that video, first step, you draw this free body diagram. As I have mentioned here, when you draw this member, you discover there are 4 unknowns. You automatically cannot solve this with just 3 equations. You need more equation. So what you need to do is sketch another free body diagram. So you can sketch this member instead. So you sketch that one, and you know that at both ends of this second free body diagram, it has pin support. So again, pin support. I cannot emphasize this enough. There are 30 of you here, and I'm expecting a few more that will come from last semester. So I cannot emphasize enough. Please understand how each support react. Okay, you might find this very kenapa lah Dr. Biba ni balik-balik dia nak cakap pasal support ni, bosan lah. Nanti you pergi tengok dekat dalam exam, saya tanda ada lagi yang pin support dia buat roller support, yang roller support dia buat pin support. Okay, so don't get confused with that, because with just that small mistake, the whole answer will be wrong as well. So make yourself familiar. There are 3 most common support that we use. One is fixed, one is roller, one is pin. So make yourself familiar with that. Doctor, the hydraulic can be considered as 2 force member. Yes. So in the video that I show you, we discover that this Bx and Dx is 0. I just want to show you how you identify them as 2 force member. So I think if you don't master your statics already, you should not be able to, it's not going to be hard for you to identify which one is a 2 force member. So this is a 2 force member. So with this, also remember that when you draw the reaction in one of the member going up, for example, the other member must have a reaction that is the same with in magnitude, but opposite direction. Again, this is Newton's third law of motion. So it must have the direction that you draw in the second member must be the opposite. So don't forget that. That can get you wrong for your answer as well if you did not do that. So make sure that you draw the reaction in the other member as compared to the other one. So in this case, this member and this member. I draw By here going upward. I can draw it going downward as well, no problem. I can draw it going downward, but make sure if you draw this here going downward, you must draw this one going upward. So everything must be logical. So in this class, try to learn from logic. Do not say that, oh, because this is the step. Okay, you must understand why everything happened. Okay, any of my subject, this is I'm trying to emphasize with student. I know I've studied in this in our education system as well. Our teacher always asks us to memorize. Okay, but then I go to Australia to study. It's totally different. We must know the logic. As long as you remember, you understand the logic, why things happen the way it is, there's no problem. I give you any other questions, you can answer this. Okay? Okay, enough saya membebel. Okay, so now 4 unknowns, we have now 6 unknowns. Okay, so now what I have 4 from this member, and I have additional 2 from this member. I have dy and also dx. But now I have 2 members, right? So I have 6 equilibrium equations. So I can solve this because I have 6 equilibrium equation. I have 6 unknown. So go watch the video, see how I solve it. So as Ashraf said just then, he identified that this is a 2-force member. So this hydraulic arm is considered as 2-force member. What is 2-force member? So if you can recognize the 2-force member, you can simplify the solution for your equilibrium equation. So the 2-force member is a member that are subjected to only two forces. It's not 3. Okay, so this is because there's another 3-force member as well, but I did not include that in this. So to only 2 forces. So for example, here the hydraulic arm AB and hydraulic arm CD is a typical example of 2-force member. So this here in this toy, this part here, this member is a 2-force member. I have a better toy here that you can see that this is a 2-force member. So it acts like a hydraulic arm. Okay, so nanti you balik UTM, bolehlah datang saya punya office, boleh main-main saya punya toys. Saya ada Lego, saya suka lah benda-benda macam tu. Alright, so 2-force member is a weightless member with force application at 2 frictionless pin. So it can be in tension or it can be in compression. So if you do your calculation, and in your calculation, the force that is being applied to that member is going to stretch them. So when it's going to stretch them, like what you can see here, it is in tension. If it's going to compress them, it's going to shorten it, it is in compression. So equilibriums for this member require it to be equal in forces and also opposite force, equal but opposite in direction, and it's also need to be collinear forces. Okay, so if we continue with that, so now if you look at the example, right after I finish this, if you don't have class, go and watch how I solve it, okay? So now that you have the other member, you can solve each and every one of these unknown. And also remember, when you have forces that acting in angle, you can solve them in the X and Y direction to simplify this, to make your life easier. Okay, so I think that's about it for the 2D. And also static equilibrium problem can also be in, for rigid body, can also be in 3D. So when it's in 3D, 3-dimension, you have 6 independent equations. So these are some of the example of the support for rigid body subjected to 3-dimensional force system. So this ball and socket, if this is the support that you have, it will resist translational motion in X, Y, and Z direction. If it's single general bearing, it will resist translational in X and Z direction, and also it will resist moment in Z and X direction. If you have fixed support, it will resist all of the motion and rotation. And for roller support, it will resist translation in X in Y direction. So to just visualize this yourself, okay? This is my beautiful drawing again. It's a pipe, okay? So this is a pipe. And I said that this is my X, Y, and this is for you to visualize it yourself. X, Y, and Z direction. But this pipe is in comes with a sleeve. So this is the sleeve that can move in Y and X in Z direction. So grab, if you want to imagine it, you grab that pipe. Can you move it in the X direction? No, you cannot. So there will be a reaction force in that direction. So I will say it's X. Can you rotate it in that axis? No, you cannot. So there will be a resisting rotation in that direction. And if you try to move that that pipe in a Y direction, can it do that? No, it cannot. So there will be a reaction on that as well. And also the same, it will prevent rotation as well. But now, can I move it in a Z direction? Translationally, I can, because there's a sleeve here. So I can move it up and down. So it won't prevent it from to move in that direction. And also, can I rotate it in that direction? This sleeve is a round shape. So I can actually take that pipe and try to move it in that, to rotate it in that direction. So this is for you to visualize it themselves. So with the reaction, you can do that. Buy something like this, a toy like this, to make yourself life easy. So I know that at the end of this toy, there's pin to make this be able to move up and down, not up and down, to rotate it in this rotation motion. But I want to see if I can move it in X direction. No, because when I try to move it in this direction, it cannot move. I try to move it in up and down, it cannot. So that's how you visualize your support. Okay, so another example. So now I have this sleeve here. So this sleeve now is in a square shape. So I have this pipe here. I now try to move it in X direction. I grab it, I try to move it to X direction. No, it cannot. So it will prevent it to move from that. It's also going to prevent it to rotate. The same in X direction. It's the same as well. It's not going to move that way. And it's not this pipe. This pipe is not going to move in X direction. It is also not going to move in Y, rotating in that axis. I can still move it up and down, but I cannot rotate it now. So I will have a rotation moment reaction there. It will prevent it from rotating in Z axis. And lastly, with this one, this is a fixed one. So this pipe is on the pole, but I fix it in there. I weld it. So it's now welded to this pole. So for this one, it will prevent it from moving in any translational direction, also going to prevent it from rotating. Okay, so that's how you visualize for 3D. And when you solve the static equilibrium equation, you can use the 6 for this one. All right. So these are some example on how to draw the free body diagram for 3D. Honestly, for 3D problem, we did not use, we're not going to use it a lot in this subject, but I still want you to know all of this reaction. We will use it for torsion, which we will learn in week 5, and also combined loading. So you must also still be familiar with all the supports. In the book that I showed you the other day, so those who just joined, I'll show you. This is the book that I'm using. It is Static and Mechanics of Materials, or you can use just Mechanics of Material by this author, R.C. Hibler. It's a very good book, simple, easy for you to understand. Okay, so that's about it for lesson 1. So what we have learned from this lesson is that we have done a few revision on statics. So a body, just a little bit of summary, a body in equilibrium is at rest or can translate with constant velocity. Before analyzing the equilibrium of a body, it is first necessary for us to draw the free body diagram. So remember that a support will exert a force on the body in a particular direction if it prevents translation of that body in that direction. And it will exert a couple moment on the body if it prevents rotation in that axis or that direction. Okay, so that's for lesson 1. And we will continue. We have 2 hours today. We'll give you, if anyone wants to ask question before we continue? Clear, Ashraf clear. Sebab dia belajar. Dia dah tanya saya pasal homework C3. Orang C1L3. Orang lain baru C1. Macam tu lah good student, okay? Sebelum saya ajar, you dah belajar dah sendiri. Ada yang dah siap, doktor. Saya tahu. So I want that. That semangat tu, okay? Saya mengajar memang saya macam mak-mak, okay? Macam cikgu sekolah. Saya paksa kamu buat kerja. Alright. Now let's continue to this very short lesson. It's about distributed load. I'm pretty sure you've learned this in oh, mana dah ni? Okay, so what is distributed load? So far, we've only learned about load, concentrated load, right? So give me an example of distributed load. Who wants to give it a try? So concentrated load, it's like if I have this book and I'm pushing it with one of my finger. Okay, that's concentrated load. Okay, if let's say I have this book and suddenly there's a wind, I don't know if there will be a wind coming or not, but if there's a wind coming, okay, and it will move this book from where its original position. So that is distributed load. So the load is not concentrated at one point. Okay, you've learned this in static as well. Jawablah saya. You know how to get the resultant force for distributed load? Yes. Okay. So if yes, this is going to just refresh your understanding. Okay, that's no problem. You've already know this. You just sit here for a refreshment course. If you're still confused, it is good because we are going to look at this together. Okay, so this is for lesson 2. For chapter 1, we are going to determine the resultant for a force distributed along a straight line, and we are going to define the location of the centroid for a force distributed along a straight line, and we are going to apply the method of composite path to calculate the magnitude of resultant force and its location for a force distributed along a straight line. So again, why do I have all these learning outcomes? I want it to be easier for you. When you do your revision, you look at all the notes that I gave you, and you study, and you look back. When you finish that particular lesson, look back at these learning outcomes. If you achieve all this, you tick all of this, means that you understand everything. So make sure when you study, look at all these learning outcomes. Every lesson, I will put the learning outcome. So by the end, when you do your revision, you know what you should understand in order for you to succeed in this lesson. Okay, so as I mentioned just then, sometimes a body may be subjected to a loading that is distributed over its surface. So for example, if I have this cantilever beam, okay, like the jumping for the divers, okay, so this is a diver here. This is the swimming pool or whatever, okay, and I have Song standing here. She's about to jump, okay, but she's still thinking, oh, should I jump or should I not? Okay, Song is applying a concentrated load at that point. And then I have suddenly Ashraf wants to give support to Song. So Ashraf come up here and he said, I will go and give support to Song. But as soon as he stand here, he got really, really scared. Oh, I can't do this. So what he did is that he starts to lie down and grab this pole. No, I can't do this, he said. What he did here is that he distributed his weight along that location. So along this section of this cantilever beam. So this is a distributed load. Okay, so if you're going to draw the free body diagram, so the weight of Ashraf, which is at the end of this, is going to look like this. It's going to be distributed along from 0 to x. And Song is going to have a point loading at the end of that cantilever beam. So that's distributed load. So a wind, wait, my network is very bad. Can you guys still see my face, my pretty face? Okay. Yeah, because the internet in this office is quite bad. Is it still lagging now? Or is it getting a little bit better? Okay. Nasrul said it's okay. Okay, so that is what distributed load is all about. So it may be subjected to a distributed load over its surface. So for example, the wind pressure of a wind on a face of a sign here, or the weight of a sand on the floor of a storage container are all distributed load. So when we're dealing with distributed load, we must be able to find the resultant force and the location of this resultant force. So how do we get the resultant force? So for a distributed load along a straight line, you all have done your calculus, okay? So we can replace this coplanar parallel force system into a single equivalent resultant force acting at a specific location on the beam by integrating from one point to another point. So the area, so if you have the function for this line, the area under the curve is going to be the resultant force. But a lot of time we did not use this, okay? We don't have to do integration because a lot of time we are going to assume that the distributed load is going to be in the ramp, like a triangle, or in rectangular. So in that case, we can just find a rectangular. We know the centroid for rectangular, we know the centroid for triangle, and we can just find the area of the area of the triangle and rectangular. But you must know, where does that come from? So it is done if we have the distributed load with this kind of shape. For example, the line is with the function fx. So if we integrate it from one point to another point, the area under that curve is equivalent to the resultant force. And the centroid, you can calculate the centroid using this equation. So the moment due to the distributed force, the sum of moment due to the distributed force must be equal to the sum of moment due to the resultant, the moment due to resultant. So this, from this equation, you can find the centroid at which this resultant force can be placed. So we need the location. So if you have a beam, we need, as we have done before, we need the location where exactly that the resultant force can be placed so that we can do our analysis, we can do our calculation. So we need this location. So you can use this equation to find your centroid for a shape, if you have a shape like this. But if you have a shape like a rectangular, or you have a shape that's triangular, then we already have that in many of the reference, and also by now you should be able to know as well. Okay, so if let's say we have this kind of, we just want to prove that we can use those equations to find the resultant force and also the centroid. So we can solve this equation together. So good job, eh? Okay, so this one you are given, this is the distributed load. It looks like a triangular, means that to one of the locations on the beam, it is the intensity is higher than the other end. So you are asked to find the magnitude and the resultant force and its location. So using this equation, if we know that we can use this equation to find the area under the curve. So if you do that integration, you will get that BL x squared and if you solve that, you will get that it's equals to BL over 2. And this is area under area of a triangle. So you can try doing this integration by yourself. So this is an area of a triangle. And then we want to find the location of this force. So if you have the beam with this length, we know that this is the resultant force. But where exactly in this beam should I locate them? So you can use that equation to find the centroid location. So if you use this equation here, you can find that centroid. So that will be BLX. and that will be equals to 2/3 of the length. So now you know that this is going to be, the FR is going to locate at the 2/3 the length of the beam. So FR here is BL over 2. So that's how to prove this, to use this equation to find the area under the curve for the resultant force, and this equation here to get the location. But as I said, most of the time we simplify and we assume that our resultant force, our distributed force, is in rectangular or it's in triangular, or it can be composite. So it can be both of them, one the triangular on top of the other one. So with that one, we can use area of triangular or rectangular, and we can use for the centroid. We know straight away that the centroid for triangular is 2/3 of the length, and the centroid for the rectangular should be at the center of that shape. So that's how we find the resultant force. So I have this example here, the methods of composite to find the resultant force for this distributed load. Okay, so the wind loading. So this is a billboard here in UTM, in front of the gate. Okay, so the window on the side, the wind loading on the side, there will be if there's a wind blowing on the sign. Okay, so we want to model this, and I can model that the wind loading on this side is looking like what I have as the idealized model here. You are asked to find the resultant force and its location. So what you can do is to divide this into 2. So you find the resultant force for this shape first, and then find the resultant for this shape. Okay, so you find that, and for this shape, the first one, we can say that the centroid will be at the center of this billboard. And for this shape, the distributed load for the triangle, it will be at the 2/3 of that from this distance to this distance. And that's how you find for when you have a composite distributed load. And then I will solve this also in Instagram, because the internet here in UTM is not very good. As soon as I have used a lot of gadgets, it will start to lag. But don't worry, I will solve this. But I want you to know, if you have this kind of distributed load with triangle and rectangular on top of one another, you can separate them and find for each shape, which one is the resultant force, where is the location for that resultant force. So for example, I have another example that I give you here. What you can do, you can find the resultant force for this distributed load. So this will be half of 60 times 4. So that's your distributed load. And where will it be? Where is going to be that location? It's going to be somewhere here, 2/3 from the lowest intensity. And then for this one, 60 times 4. So that's going to be the FR. So this is FR1. And then we have another FR2. That FR2 will be at the middle of that distributed load. So that's FR2 is going to be equal to 60 times 4. That is the distributed, that is the resultant force. And for this one, find for this one first, which is 40 times 5. divided by 2. And that's going to be FR3, and that's going to locate, no, 2/3 of that. And then find this one. So that one will be 60 times 5. That's 300 pound. And it's going to locate at half of that, in the center of that distance. So now you will have something like this, all going downward. And then you can start doing your analysis, static equilibrium. Then you get, you have fixed support, fixed deposit. I was about to say fixed deposit. I'm thinking about money. All right, so AOY, and then you have OY, OX, and then you have MO. Fixed support's going to, it's going to resist all motion. So you have here FR4, you have FR3, FR2, FR1. Okay, so you can see that, okay, now I have all forces acting downwards. So I wouldn't have any, this AX is going to be equals to 0. But this is going to, if you sum forces in Y direction, the sum of all this is going to be equals to this, but opposite direction. For a moment, all of these are going to rotate it. It's trying to rotate it clockwise rotation. So as I said in one of the video, if you want to imagine where it is going to rotate, get your pen like this. And then put your finger in at the pivot point. So here, my pivot point is here. This is my fixed support. So I have forces acting downward. So that is going to cause rotation. It will try to rotate it to clockwise rotation. So if your sign convention is, you said that positive is anti-clockwise, that is going to be negative. It depends on how you assign your sign convention. If it's for me, I always assign anti-clockwise as positive sign convention and clockwise as a negative sign convention. So, but I will look into, when you solve your problem, I will look at how you assigned it. If you assigned it clockwise as positive, you should mention it in where you write down your solution. Okay, so that's a very simple revision on distributed load. So in summary, a simple distributed loading can be represented by its resultant force, which is equivalent to the area under the curve, under the loading curve. This resultant has a line of action that passes through the centroid or the geometric center of the area or volume under the loading diagram. As I have mentioned, it's very rare that you are going to be given a function aligned with a function with irregular shape. But I want you to know how we get all those equations, how we get to that solution. So we need to do integration. But in exam, you're always going to be given rectangular or triangular. Okay. We still have about 1 hour. I will give you about 5 minutes break, and I want you to come back, and we will continue with internal forces. But before that, anyone have any questions you want to ask? First week, mostly students don't have questions because you've already learned this in statics. Coming to second weeks, I will expect more questions from you, okay? All right, so let's have a 5-minute break. I will time this with a timer, and after 5 minutes, let's come back and we will discuss about internal loading. All right, siapa nak pergi toilet, pergilah sekarang. Okay, so enough break. Kita sambung lagi. Tomorrow we will do tutorial on the homework that I gave you. So today we will finish all the revision on statics. And next week I will we will have quiz number 1. So quiz number 1 will be on the reaction forces and also internal forces. How you determine internal forces. Okay, so ready? Good. Since all of you have already mastered statics, I want you to answer what is internal forces. It's already in your notes, but I want one person to talk about it. Where is this internal forces come from? Any volunteer before I call out a name? Jangan malu-malu. No right or wrong. I will not shame you if you are wrong, but I will applaud you for trying. Forces that act in the same body, forces that act in the same body. External, external can be forces that act on the body as well. So as I have, but thank you, Nasrul. So external forces is acting on the body by some other object, whereas internal is the forces that is what you said is act in the same body. Okay, I get what you are trying to say there. That's correct. Okay, but where is that come from? What are all body made of? Everything. Our body, a phone, metal, matter. So it comes from a structure with a building block of atoms. Okay, so everything. So like this steel, how to say it? This steel ruler here is made of stainless steel. So stainless steel is a combination of carbon with iron with a few atoms of carbon inside. Okay, and they arrange themselves in. So that's a good thing when I'm teaching material science as well. So the atoms inside these materials is looking like this. So they arrange themselves in this arrangement. And as we know, atoms are all having vibration. So atoms vibrate. So the one of the atoms exert force to the other one, and the other one will exert the same force. That's why it doesn't come up in our calculations of equilibrium, because they cancel each other inside the materials itself. So that is the internal forces. So we did not include them in our static equilibrium equation because they did not contribute to motion. Is that clear? But we still need to know them because we want to know how strong the materials. Can the materials sustain if you apply external force on it? So the internal force is actually what resists it. So if I put a force on this steel, right? So I put external force on this steel. This steel will have a resistance. If I try to bend them like this steel actually has a resistance not to bend. So the internal forces is helping them not to bend. So that is internal forces, the forces that act in the same body. So it comes from the reactions of atoms inside these materials. So the vibrations between the atoms are going to exert force within themselves. So we need to know external forces in order for us to analyze it. So in mechanics of solid, internal forces is very important. We need to find out the shear force, the axial force, and also the bending moment. And when we study twisting, so when we try to twist the body, for example, shaft, the car drive shaft in the car, it is going to be the external force will be twisting the body of the materials. So these materials will have a torsion, will have internal forces that will try to resist that twisting. So for example, if you look at this is the shaft, for example. External force, external torque is going to try to twist them. So the body of the materials itself, the atoms inside the materials, is actually trying to resist it. So it will try to twist it back. And that's the things that we will need to learn. We will need to use in our analysis in mechanics of solid. So here, the lessons learning outcome is to define what is internal forces and to use the method of section to determine the internal loading in a member at a specific point. So as I said in my first class, the class will be more beneficial if you think together with me. Okay, it's not just me who's giving you information. You think, and we discuss this together. You're already in your 20, 21, 22 years old. Okay, you're an adult. You don't need a teacher that's going to just spoon feed you. That's not fun in learning in that way. You must be able to think as well. So when I ask question, I like if you get together with me and we discuss it together. Okay. Okay. So what's the difference between internal forces and external forces? So internal forces is forces which act on one part of an object by another part of the same object. So it's the forces in the body of that material itself. And external forces is the forces which act on an object by some other object. So for example, this here, when we applied external forces, you can see this is what happened inside the materials. Okay, so we apply external forces. The intermolecular forces between the atoms is going to try to resist that motion. So internal forces is the forces act inside the body itself. Okay, so if we know these internal forces, only if we know these internal forces, when we apply external forces, internal forces is resisting. So we need to calculate this. We need to know how to calculate these internal forces because we want to know if our materials can actually sustain the force that we are applying. So for example, again, come back to the crane, the pin in this crane. As I said, the pin in this crane is going to be resisting this load that we applied here. Okay, and we will have the reaction force there, and that reaction force is going to stress that materials. It is going to make that materials deform. Even though we said it's not deformed, we cannot see the deformation, but it is going to start to want to deform anything as well. Like if you have plasticine, you put a force, the materials is going to deform. It's going to change shape. The internal forces is going to want to stop that from happening. So if we can calculate that internal forces, we can actually calculate how much stress we put on that materials. And if that material has, for example, this material has a inherent properties in which it can only sustain 200 megapascal, for example. And if we apply an external load that exceeds that 200 megapascal, this materials is going to start to fail. Clear? Okay, so in our net force on a system, vector sum of internal forces, the net force of a system should be the calculation of vector sum of internal forces plus external forces. But as I said, the vector sum of internal forces is zero because from the Newton's third law, internal forces will occur in equal and opposite pairs, so they contribute nothing to the sum. So they did not influence the system motion. So that's why you did not see them in static equilibrium equation. We use static equilibrium equation to determine them, but when we do method of section. But when we calculate the system motion, we did not include them. Okay. The design of a structural member, even though they did not influence the system motion, the design of a structural members require an investigation on the internal forces of the member to be sure that the material can resist and carry the load. So this is just for your information. What is the, as I said, Newton's third law, second law of motion, first law of motion. As an engineer, you must be able to state this. So jangan malukan saya. Orang lain tanya, what is the first law of motion? Newton's first law of motion. You should be able to answer it and give them an example, okay? That's how my students should be. Okay, so we can calculate internal forces using method of section. But I want you to imagine this beam here. So this beam, I said that is going to be, I have 3 sections of this beam. And I weld them together. So I have this number 1 here. So I have section number 1, section number 2, and section number 3. They are from 3 different parts. I weld them together. So now this weldment is what support? Can anybody answer this? I can equalize them as which support? Fixed support. Very good. Okay, so it is fixed support. So this is how you want to visualize to calculate these internal forces. Okay, so this is, oh, I've already have this in my notes. Okay, that's good. Okay, so technically all beams are fixed together through intermolecular forces to form the continuous body, as I said with this one. So you imagine all the atoms inside this are arranging themselves in this form, in these crystals, in this structure. So all of them are actually, technically, we can see that it is it's fixed together through molecular forces to form this continuous body of this roller. So with fixed support, if I try to, if I put it, look, separate them, okay? Now, if I separate them, we said that with fixed support, okay, with fixed support, it will resist all motion. It will resist all translation motion, and it will resist all of the rotational motion. So it will resist both motions. So if we do method of section and we section it to this part here, and we reveal the reaction support, okay? This is if we don't think about internal forces. If we reveal the reaction forces, there must be force, it must be resisting in X direction, Y direction, and also the rotation motion as well. So if you do that with all of the section and reveal that, that is how you look at internal forces. So you look at this part. We'll just look at this part first. Okay, so this is pin support. So there must be A, if I said this is A, B, C, and D. Because we just look at this part. You just imagine that this part here is a fixed support with another portion here. So if I just draw the free body diagram of that, there will be AX, AY, and B by, bx, and also moment to resist that motion. So the same with the others as well. So with this one, it's fixed support here, fixed support here. So if I reveal that support reaction, it will look like this. So the same with this one, it will look like this. So that's how we do method of section. So we reveal the internal forces by assuming that there is a fixed support, there is a fixed support there. So is this one clear? You need to be able to visualize this. So we make section cut along any portion of the beam. We have reaction forces that will result from fixed support. So, but however, since these come from within the structure, we call them internal forces. So this is internal forces because it is in the body or in the rigid body itself. Okay, saya pun penat menerangkan. If any questions, put it in that chat box. So there are 3 internal forces corresponding to the 3 reactions of the fixed support. So we name for the one that acting normal to the surface where you cut them, we call them normal force. And if it's parallel to that surface, we call them shear force. And bending moment is when they try to resist rotation. So that's the 3 fixed support, 3 internal forces that we're going to use here. In this image here, you can see torsional moment as well. So torsion is also internal forces when we try to twist any materials. So basically, there's 4, but for the the one that you have learned in statics, you only learn 3, right? Am I correct? Okay, so you learned that normal force, shear force, and bending moment. So everyone, I expect to know how to calculate all these. So when we do method of section, the internal loading can be determined. We can determine internal loading with a method of section. So for example, here I have this cantilever beam, and I have a few forces acting on the beam, P1 and P2. So this method involves analytically cutting the truss into sections, solving force, and solve using static equilibrium for each of the section. So here, if I section it at point at section AA there, what I need to do is to section them and reveal the internal forces and solve this with static equilibrium equation. Everyone can do this? So with the sign convention, so if the materials is going through external forces that is going to elongate them. So when we try to elongate something, so if you try to elongate, for example, this rubber band, and this is a good example, okay? We try to elongate this rubber band. The internal forces is going to try to resist that elongation. So the resisting force, we put them in the sign convention as positive. So you look at this, it's probably going to be confusing to some of you. We said that, why is this going that way? It's positive. And if you do the static equilibrium going to the left, it's going to be negative. No, because this, for internal forces, this is resisting this force. So this is going to be positive for this section, for the second section. So this is section 1, this is section 2. So for section 1, the external forces is going that way. So this materials is going to, internal forces is going to resist that motion. So the one that they resist, when it's resisting, we put a sign convention as positive. And if we look at the, let's look at the shear first. So if the materials are going through shear forces, so there is a force that going in the y direction. Okay, so this, for example, this one. So there is a force going in a y direction. The internal forces is going to try to resist that one. So it wants to stay in its position. So it will resist that motion. So that's why going down here is positive. Okay, but you will get confused this when you do calculation, but I will unconfuse you. So again with the same as well with this one. Okay, so it's if the shear force is going down, the material is going to resist it by going up. So it's going to try not to deform. So by not deforming, it needs to resist the force that you are putting on them. So for example, another one here, if bending moment, as I said just then, we put a force that is going to bend these materials, okay? But for a lot of structural materials, you did not see them bending. The deformation is very, very small that you cannot see them, but they are actually bended. So the materials is going to try to resist. If it's going this way, it's going to resist that. So if this is positive, I said anti-clockwise is positive. For internal forces, in this section itself, it's going to be positive if it's going this way, because it is resisting this force here. And the same with this section. This section has, this is the moment, it's going this way, like the concentrated moment is going that way. And this one, the internal forces is going to try to resist that. So this is positive, this is positive, this is positive for internal forces. But when we do calculation using static equilibrium equation, we do it as normal. So if we take this as an example here, okay, we still have 20, not 20 minutes, about 20 minutes like that. I give you 5 minutes, maybe 10 minutes to do this by yourself, and let's post it in WhatsApp group. Okay, so we still have about 20 minutes. Do this for 10 minutes and then post it in WhatsApp, and I will discuss that with you after 10 minutes. Okay? All right, so I will put a timer, 10 minutes. I'm expecting at least 4 or 5 of you try to answer this. As I said, when you cut it to its section. You cut it to the section. You use static equilibrium equation as normal. If going down is positive, it's going down negative, going up positive, and going to the left and right is positive and negative. So just do it as normal. Forget about the sign convention. I will explain about the sign convention after you do it. All right, so take 10 minutes and do that. Everyone should do it. We are here to learn, okay? Don't just wait for your friend to do this for you. Just do for point B. You don't have to go with point C. Just do for point B. Okay, so I can see that again, Ashraf already share his answer. Very good. I like this. You're very interactive in my class. Normally, students that I remember them. You as I said in the previous class, make sure I remember you. If let's say one day in the final exam you needed half mark to actually get an A or A minus, just half mark. But if I know you're not cooperative in the class, I cannot help you. You know, I I need to be able to know you, to know your attitude towards the subject, to know that you are actually interested, that you are a good student. Okay, so for me to be able to help you in a certain way, not too much, just like that, I can look back at what have you done, the homework you've done. Okay, if I decide you deserve this half mark. Okay, so make sure I remember you. Okay, so for this question, the first step, you should draw the free body diagram. So if I draw that free body diagram, I know that this is a roller support. So you will, good job. So this is a roller support. You isolate the member from the rest of the world, and I have roller support here. So it will prevent it from moving in the Y direction, but it's not going to prevent it from moving in the other direction, and also rotation. My ear pod I have to take it out. Just wait a little bit. Boleh dengar tak suara saya? Yes, okay. So draw the free body diagram. And I have AY here, and I have this one is pin support. So DY, DX, AY, and I have 6 kilonewton here. You are required to find the internal forces at this point, just the left to that 6 kilonewton, and the right, just the right to that to the 6 kilonewton. Okay, so because I only need this section, you can solve for AX, DX, DY, AY, it doesn't matter. You can do that, okay? But because now I only are required to use, I only needed to use this section, the left section of this beam. So I can just solve for this one. So I can just solve and find what is AY. So to find AY, you can sum moment at point D. And I said that it's going to be all equals to 0. Going anti-clockwise is going to be my positive sign convention. Okay, so that would be what, wait a moment. So I have this is going to cause the 6 kilonewton is going to cause anti-clockwise rotation. No, clockwise rotation. Am I correct? So that's going to cause clockwise rotation. So that's a negative 6 times 6. Its moment arm is point D here. So, no. Point D, the pivot point here, this is, so that's going to be positive. So kalau saya salah, just let me know, okay? So that's going to be positive. So its line of action is here. The perpendicular distance is this distance. And then I have the 9 kilonewton meter, the concentrated moment, and that's going to be positive as well because it's going anti-clockwise. So that's 9. And I have this
reaction force is going to want to rotate anti-clockwise. So that's going to clockwise. So that's going to be negative. So AY times 9 equals to 0. So that will be you will get your AY equals to 5 kilonewton. All right, so we now have this part here, the left section of this beam. So you can do method of section. You section it at that point B and draw that free body diagram. So that's will be like this. 3 meter. And here I have my AY. That's 5 kilonewton. And since we said that this is a fixed support here, intermolecularly, they are fixed together, we will have, and it's in this section, so you can draw your direction for your section as the always draw it as the positive in the sign convention, as the sign convention that I give you here. Okay, so if you do left side, you use this positive sign convention. If you take the right section, you use the right section positive sign convention. All right, so here for this, the positive will be NB, and then this is VB, and the moment will be, bending moment will be MB. And you solve this with static equilibrium equation as well. Now we have 3 unknowns, we have 3 static equilibrium equation. Do it as usual, as have a look at, have no more space. Oh no, this is not, yeah, this one. Okay, so this is the free body diagram just then. 3 meter, and B, VB, and then MB. I have AY equals to 5 kilonewton. So you can sum forces in Y direction, X direction. Sum forces in X direction equals to 0. I said this is positive. So that you can see that NB is equals to 0. And then I have, I can sum forces in Y direction, and that will be equals to 0. And I said going up is my positive sign convention. So I have 5 kilonewton. And then I have going down is the shear force, and that's going to be equals to 0. So shear force is equals to 5 kilonewton. So this is what that sign convention means, okay? You can see that it is going down, but it is 5 kilonewton. It's positive. So as you can see here, we said for this section, going down is positive. Going up on this section, going up is positive. Normally, when it's external force, going down is negative. But with internal forces, going down, if it's the left section, it's going to be positive. So that is what that sign convention meant. Okay, and when you can finish up by summing moment at point B, positive. So that you will get 15 kilonewton meter, and that would be positive as well. So try that. I will post that solution if you need it in Instagram, and I will post this solution as well later, maybe this afternoon. We have run out of time. Is internal forces clear for everyone? Doctor, for point D, fixed support. It should have D. Is it point D? Oh, yeah. For point D is fixed support. Let's go back. Yeah. No, point D is pin. Look. Point D is pin. It should have dx, dy, md. That's the kilonewtons, it was already md. So that point D, if we look back at, I'll reshare that. So you look at this, this is pin support. It's not fixed support. Fixed support when it's like the cantilever beam I showed you just then. All right? But there is a concentrated moment being applied at that force, at that point. So this 9 kilonewton meter is a concentrated point moment. It is not from the reaction force. No problem. As an all right or wrong, we are learning together. Okay? Yes, so don't be tricked by the base of the pin. Yes, the base of the pin is fixed, but the body is not attached to the base of the pin. It is attached to the pin. Okay? All right, so I think that's it for today. Any questions you want to ask, free to do so in Instagram, in WhatsApp. I like an open discussion in WhatsApp. So if you have question for me, I prefer you share the question with the other students so everyone can be aware with what's happening. Okay? Any questions before I end this session? Okay, so far so good in my class. All right, guys, I'll see you again tomorrow. Don't forget, submit your homework, and then we will discuss together about the homework tomorrow. I saw 4 groups already submit, so there's 2 more. Please submit today or tomorrow morning. All right, have a good day. If you have class, enjoy your class. Bye, guys. Assalamualaikum.